would like to introduce this month's speaker. We have Marvin Humphrey, who is going to talk about the paper Advances in Dataflow Programming. Welcome to the July Papers We Love San Diego. Go for it, Marvin.
Hi, everyone. Thank you. The essential quality of a Dataflow program is that it can be represented as a directed graph. And now let's glance over a handful of Dataflow programs just to get a sense of the possibilities. This is a Dataflow program which performs a simple arithmetic computation. It takes an input x and an input y, sums x and y together, divides y by 10, and then multiplies the results of those operations to get a final output. This program is not in any particular Dataflow programming language. Instead, it's an idealized representation that you might think of as pseudocode. Here we have a somewhat more sophisticated program written in Pure Data, or PD, a Dataflow-ish programming language used primarily for audio DSP. What this program does is take input theoretically from a theremin. It's basically, it will take any monophonic input. The theremin is that spooky science fiction instrument that goes like woo, woo. And it quantizes the pitch and amplitude from the theremin or monophonic input and converts those values to a stream of MIDI messages. I say that PD is Dataflow-ish because despite the name Pure Data, it is not a pure Dataflow programming language. PD programs cannot be represented as directed graphs, at least pure directed graphs, since, among other things, they make use of global variables. However, it is possible for subgraphs within PD programs that they might be realizable as pure directed graphs. This is also a Dataflow program, and it also describes a directed graph. It just uses text to specify that directed graph. And that is not unusual in the slightest. Dataflow programming has been around since the 1970s, but Dataflow visual programming didn't become popular until the 1990s when reasonably priced workstations became powerful enough to run visual editors. The early Dataflow programming languages were all text-based. This is written in Apache Pig, which is a modern Dataflow language, powered by Apache Hadoop and targeted at big data processing, to use a term of art from a couple of years ago. This sample program is taken from the O'Reilly book, Programming Pig, by Alan Gates. And what it does is count the words from a text file containing the nursery rhyme, Mary Had a Little Lamb. And here we have a graph, albeit one which is stylized and abbreviated, of how Pig might actually implement the word counter program, assuming that Pig is configured to use several workers. Yes, this is utter and complete overkill in terms of the resources you're bringing to bear in order to count the words in Mary Had a Little Lamb, but we'll explore later why Dataflow algorithms are conducive to scaling through parallelization, of which this is an illustration. I mentioned earlier that the Dataflow programming paradigm is to represent the program as a directed graph. I didn't explain what a directed graph is, so for the benefit of those who may be less familiar, here's a little review. A graph is a data structure, a collection of nodes and vertices, which are nodes or vertexes, which are connected by edges or arcs. And a directed graph is a specialization of that where the connections have direction. It is differentiated from an undirected graph where the connections are bidirectional. The connections in these visualizations on the left, we have several directed graphs on the left, all have arrowheads indicating the direction of information flow or token flow. In an undirected graph, they would typically be bare lines instead. The term node can be substituted with vertex or point or junction. Similarly, edge might be, or arc might be link or line or connection or wire or cable. In popular usage in computer science and graph theory, vertex and edge tend to win out when you're talking about graphs of unspecified type or about undirected graphs. But if you're talking about directed graphs, people tend to use node and arc more commonly. And since in Dataflow, we're talking about directed graphs exclusively, we're going to stick with node and arc. Here is a programmatic representation on the right of a directed graph. There are two collections. The first is a bag of nodes just named 1, 2, 3, 4, and 5. The second is a bag of directed edges. The first directed edge points from 1 to 2, second one from 2 to 3, then from 3 to 1, 2 over to 5, 4 over to 5, and then that loop at the end is 5 pointing to itself. So, in these directed graphs modeling Dataflow programs, what do the elements represent? Well, for starters, the node stands in for a unit of computation, which could be as small as a machine-level instruction, such as this mult node that we have on the left there, symbolized by the asterisk. Or in more coarse-grained data flows we'll get to later, it could be a function of arbitrary complexity. A node takes one or more inputs. In this case, it's taking 2, and it produces one or more outputs. In pure Dataflow, the only way to get information into or out of a node is through its ports or its arcs. Global variables are disallowed in pure Dataflow. An arc you can think of as a pipe or a path through which data passes. That's the obvious visual metaphor. But more importantly, there's a conceptual insight here. Arcs express data dependencies between nodes. A token is a unit of data of unspecified type or and value, or more precisely without regards to its type and value. And a port refers to the boundary between a node and an arc. So there's two types here: the input ports, which are at the top of that thing where the input tokens are being received, and the output port where the output is placed. Not everyone uses the term port. In fact, the paper that I'm presenting didn't use that. It prefers input arc and output arc. In any case, while the book that's associated with the video I linked to, that one uses port. In any case, the concept of having input ports, output ports is a useful concept, as we'll see. So let's study the sequence of events that unfold as a node activates or fires or executes. That all means the same thing. This is a pseudocode mult node, as indicated by the asterisk, and it performs multiplication. It has 2 input ports and 1 output port. When the program starts, the node is in a state of waiting to become fireable. After some unspecified amount of time, a token arrives at one or the other of the input ports. It doesn't matter which one. After some unspecified amount of time, a token arrives at the other input port. At this point, the node has acquired the quality fireable. After some unspecified amount of time, the node fires, which involves a few steps. First, the node absorbs the tokens from its input ports. Then it performs its defined calculation or computation. It takes the output of that computation and places it on the output port. At this point, it has ceased firing and has returned to the state of waiting to become fireable once more. Crucially, an indefinite amount of time elapses between each step in this playlist, according to Dataflow theory. And that is important because the execution sequence of a Dataflow program is not determined by a program counter ticking through an ordered series of instructions, as we would have on the right in that von Neumann-style program on the right, but is instead contingent upon data dependencies becoming satisfied. Let's explore what that means. On the left, we have the Dataflow pseudocode for the arithmetic computation. On the right, we have the equivalent program expressing the same thing in an imperative von Neumann-style pseudocode. which is a sequence of instructions for the computer to follow in excruciating detail. So in time unit 1 of the von Neumann program, x and y are summed and the result assigned to A. In time unit 2, we have y divided by 10 and assigned to B, etc. So it takes 3 discrete time units for the program to generate its result, and the executions assigned to each of those time units must be executed in order. But when those programs, at least theoretically, optimizations notwithstanding, but when these programs start up, they have to wait for the input values to arrive. And arguably, the von Neumann program can't even start before input is ready. But let's finesse that for now and just proceed with the thought experiment. What if y shows up before the value for x shows up? Say again? It will be divided. Yes, the programs will behave differently at this point. So the imperative program cannot proceed because the instruction which is queued, that first one, still has a data dependency on x, which has not yet been satisfied. However, the Dataflow program on the left can distribute y to the input ports of both the sum and the divide nodes. And the divide node has already received the input token for 10, since that was prepared to begin with. And now that the divide node has received input tokens at both of its input ports, it has become fireable and it can proceed with its step. So meanwhile, the imperative program is continuing to block, but the divide node can then finish its computation and place its result on the output port and prepare it so that it's now at the input port for the mult node. Eventually, X is going to show up. Both programs are going to finish, but the Dataflow program had a head start. And this doesn't sound like much in the context of simple integers, but let's imagine for a moment that rather than simple integers, X and Y are instead extremely large vectors. So that now those sum, divide, and mult nodes represent costly vector operations. Now we're talking about real savings if you can get every element in that giant Y vector divided by 10 while the X vector is taking its own sweet time showing up. And this illustrates an inherent strength of Dataflow programs over von Neumann style programs. Dataflow naturally reveals opportunities for parallelism. And this arises from 2 factors. The first is that because Dataflow is superior at recognizing when all data dependencies have become satisfied, Dataflow programs realize sooner when it has become possible to launch a parallel operation. And the second is that Dataflow programs naturally tend to prevent styles of memory access which would preclude parallelism. So the von Neumann style memory model starts off with the assumption that all memory is accessible at all times and mutable. This creates data dependencies where none previously existed. The variable A is assigned in the first line of our sample code. Now when compiling, we have to determine whether what has been happening to A is relevant to us. Is A still in scope? If it's still in scope, are we actually using it? Can A be assigned to more than once in our program? Who has the privileges to update A, or more precisely, the memory location at which A binds to? Could that memory location have been tampered with by other threads executing in parallel? And these are all solvable problems, but it would be nice if we didn't have them. So in a pure Dataflow model of programs, model where we model the program as a directed graph, we start from a different place. There are no global accessible mutable variables. There may be compile time constants, but that can't be differentiated from the program code itself. Our chief concern is with mutable globals, or at least mutable non-locals. It's not that this change of memory model solves all our problems, but it gives us a different set of problems to start from. And all inputs and outputs within Dataflow are constrained to within nodes and arcs, something which seems very natural when you're modeling a program as a directed graph, but is decidedly unnatural under von Neumann. So in a sense, you can think of Dataflow programming as a subtype of functional programming, although really it's the nodes themselves that are functional. The complete Dataflow graph is not necessarily. With all of the advantages of functional programming, or at least some of the advantages of functional programming in terms of provable isolation and immunity from side effects, the nodes represent functions. The input ports represent the formal parameters. So this programming paradigm, where we represent programs as directed graphs, why call that Dataflow? As we talked about before we got started today, data's flowing everywhere in every program. But perhaps, let me flip that on its head and say, why not Dataflow? We have this powerful programming paradigm where we represent programs as directed graphs because directed graphs are a fantastic construct for representing data dependencies. And many advantages flow from having this capability. So we need a name for this paradigm. And well, this technique of specifying how data flows seems to be a complement to the von Neumann paradigm of specifying how control flows. So why not contrast it with Controlflow and call it Dataflow? Because arguably, Dataflow programming and von Neumann style programming are two extremes of a continuum. We have the program as directed graph versus the program as a sequence of instructions. We have execution following the satisfaction of data dependencies versus execution following the advance of a program counter. We have maximum memory isolation thanks to the constraint of elements within the graph versus a starting point of globally updatable memory. So this continuum is similar to the continuum between imperative and declarative paradigms. Similar, but not quite. In the imperative paradigm, you tell the computer exactly what the sequence of events, instructions it should execute. While in the declarative paradigm, you give it a set of goals and let the computer figure out the details. The declarative programming is really a higher level of abstraction. But a Dataflow graph, a Dataflow directed graph, is not necessarily a high level of abstraction. Dataflow was, in fact, originally conceived to be at the instruction level. And the original purposes of Dataflow programming languages was to power Dataflow hardware in the 1970s, which would compete with von Neumann hardware, and for which Dataflow graphs would serve as machine code. In his 1977 Turing Award lecture, John Backus, the designer of Fortran, posed the question, can programming be liberated from the von Neumann style? And Backus's aim was primarily to advocate for the functional programming paradigm, but Dataflow hardware was mentioned multiple times in his paper as an alternative, a contemporary alternative and competitor to the von Neumann architecture. And this is how early Dataflow programming languages developed as support for Dataflow hardware. Conventional imperative languages were modified by limiting support for variable assignment, by fiddling with scope and locality. And when the results could be compiled down to Dataflow graphs, again, Dataflow graphs as the machine code of Dataflow hardware, those programs acquired wondrous properties. Regrettably, though, one answer to Backus's tormented question is Dataflow ain't going to save you. Because designers in the 1970s ran into seemingly intractable problems with Dataflow hardware. And this is why you don't see Dataflow hardware as a competitor to von Neumann hardware today. One of the biggest problems was that although directed graphs could reveal potential for theoretically infinite parallelism, of course, in reality, the number of parallel operations that hardware can support is always finite. This had consequences such as programs which could be proven never to deadlock, but when you run them on actual hardware, they would deadlock nevertheless. Another problem is that applying the insights gleaned from Dataflow graphs at the instruction level requires a lot of monitoring overhead. How you know when your input tokens have arrived and a node has become fireable is a complicated story that I've chosen to skip over tonight for the sake of brevity. They describe a couple of systems in the paper for actually doing that. They don't describe the hardware that actually implemented those instructions, but they are rather elaborate systems that, say, require a stream of information to be flowing the other direction to allow nodes to know when they are becoming fireable. A different sort of problem arose in that the constructs for iteration in Dataflow programming languages were often verbose and awkward. This really becomes obvious when you try to represent iteration visually, as we'll see in a moment. And that meant that programmers accustomed to imperative constructs, they found it challenging to adapt themselves to the looping idioms in Dataflow programming languages. But the biggest problem was really the success of the competition. Von Neumann processors were increasing at the pace of Moore's law. Pipelining, speculative execution, optimizing compilers, all made it possible to discover and exploit parallelism within the context of von Neumann. And Dataflow just couldn't keep up. And so Dataflow development flagged for a few years during the 1980s until some new areas of interest rose to prominence in the 1990s. Coarse-grained, what we call coarse-grained Dataflow and hybrid Dataflow. So on the left, we have an implementation of the factorial function in a Dataflow-directed graph with nodes representing machine-level instructions. There are certainly many algorithms which can be realized elegantly with Dataflow graphs or in visual programming languages in general, but this ain't one of them. The main challenge here is looping constructs. That's what those switch and merge nodes are actually implementing. That's the actual looping construct. Actual Controlflow in general is a weakness of, or Controlflow is a weakness of visual programming languages in general. It's not just Dataflow, but Dataflow has this problem along with many other visual programming languages. But looping works just fine in text-based imperative languages, or for that matter, in text-based functional languages. Indeed, the task of writing a reliable factorial algorithm is perfectly well suited to imperative languages. So why not just code that node up in an imperative language instead of fiddling with something like that monstrosity on the left? And then let some high-powered von Neumann compiler optimize it to within an inch of its life. And then why not just stuff the result of that into that abstracted factorial node there on the right? That node on the right there is still a well-behaved Dataflow node. There is no global memory access. I mean, that's just a factorial function like you would write in one of Lisa's computer science classes. So it's got no global memory access, well-behaved local variable isolation. Parallel instances of that are always possible. So we can still apply Dataflow analysis at levels above that factorial node, and we don't need to apply fine-grained analysis. And these techniques of hybrid Dataflow and coarse-grained hybrid Dataflow, referring to inserting nodes which are written in imperative languages or other languages into Dataflow graphs, and coarse-grained Dataflow, where the nodes represent something greater than machine instructions. Those concepts are what, along with improved visual programming editors, revitalized Dataflow research and development in the 1990s. So with that in mind, let's return to our PIG program and putting Dataflow to work in the problem space of crunching big data. So what this PIG program does is read in lines of text from a text file. Like Pat was complaining about earlier, a lot of these programs are designed to take text input, and it tokenizes those lines at word boundaries and then updates a global mapping of words to word counts. That's the representation of the Dataflow program on the right there. That actually is not the full Dataflow graph. It would be more complicated than you see here. Mutating a data structure is disallowed in Pure Dataflow the same way it is in functional programming. So you would have to employ, in order to get looping constructs in Dataflow, you have to employ a trick like what they describe in the paper is you're doing what looks like a for loop, but instead of updating the program, they actually say next A. And so A on every iteration through the loop is a new A. It's not the same A that you're reassigning to, it's a new variable. And because of that, you're not violating the ban on assignment. So, so I'm not showing that here in there, but so now but this is enough so we can look at how PIG implemented this program. What it's done is assigned along the top there, one worker per line to the task of tokenization because it is recognized that the task of tokenization is parallelizable. And then the output from that tokenization gets sent to one of two counting workers. The one on the left is handling the words from the front side of the alphabet, and the one on the right is handling the words from the back side of the alphabet. So we have had a little lamb on the left, and we have Mary was white snow on the right. And what this example program and illustration illustrates is how Dataflow, the Dataflow paradigm, lends itself to programming in a cluster. Nodes in a cluster, like nodes in Pure Dataflow directed graph, do not share global state. At least not naturally. You have to have, they don't have they're on different machines, so they have to pass messages between them. And the arrival of data at a node in a cluster typically activates that node, which is the same model as we have in Dataflow with the activation of a node as the data arrives at its input ports. So in a pure model of Dataflow, the nodes are considered to be FIFO queues of infinite capacity. That doesn't work well in practice because execution is too controlled by external events. If too many events arrive, too many events meaning tokens, then you exceed the capacity of the queue and your slowest node bunches up. But nevertheless, Dataflow analysis reveals opportunities for parallelism, and that works well for managed workers operating in a cluster. And this is truly coarse-grained Dataflow, extremely coarse-grained Dataflow, since the operations are entire service workers. It's also hybrid Dataflow, since it's not turtles all the way down, it's not Dataflow all the way down. Some of the innards of these workers are implemented using von Neumann languages. Some are all. Okay, so now going from big data, now we're going to zoom down in level. We're now looking at DSP systems. Here is a simplified version of the Pure Data Theremin to MIDI program I showed you earlier. On the left is a version assembled in the PD visual editor, which is what people are expected to work in. On the right is the source code, which is generated by that editor. When we examine the source code, we find that it is pretty much a traditional representation of a directed graph. At the top, we have a number of elements which correspond to nodes, and at the bottom, we have connect elements, which represent arcs between the nodes. So just looking at those that connect, that first one says 0010. What that represents is the first number is the identifier for the first element. Then the second number is the port number on that element. The third number is the identifier of the element that's pointing at, and the fourth number is the port on that element. So we are moving from the first in that first connect corresponds to that first vertical line there. And there would be an arrow if this was a directed graph, but all of the flow in this thing is from top to bottom. We start at the analog to digital converter, which is that ADC at the top. And then it passes data via that first connect arc to the fiddle object there. And that's what that connect does. It's connecting from the object 0 at the first port to object 1 at the first port. Okay, then we've got this. What the fiddle object does is it's actually doing all the heavy lifting in this program. It's using FFTs internally that generate raw pitch and amplitude information, converting from the time domain to the frequency domain. After that, we have an unpack object, which does destructuring, basically a utility node. The Moses object is a gate. It's, the idea is it parts things. It's a thresholding thing. Ha ha ha. So the 1 is the threshold here. What this means is that anything which is less than 1 gets sent to the left port. Anything that's more than 1 gets sent to the right port. Since the left port is empty, basically anything less than 1 gets thrown away. Then we have that node and amplitude. Those are actually slightly different. Those are basically just readouts. If I had PD running, and I was actually doing that, you would see the node that would be changing as the input changed. And then control out, that's just outputs for MIDI channels. So while these objects are nowhere near the size of a worker in our pig-powered cluster, they are still much larger and more complex compared to the machine-level instructions of that fine-grained data flow. And just like that pig example, these nodes are not just coarse-grained data flow, but they're hybrid data flow as well, because pure data is fiddle, unpack, Moses, etc. Those are all implemented using good old von Neumann C. So Dataflow has found a niche in DSP specification for a few reasons. One is that the directed graph is an apt physical or a metaphor for the physical for electrical signals flowing in a physical circuit. In an electrical circuit, the signals only flow through wires, or at least in a well-behaved electrical circuit, the nodes only flow through wires. There's no analog for mutable global variables. And another reason that Dataflow is copacetic with DSP is that Dataflow lends itself to a particular kind of analysis called synchronous Dataflow. And under synchronous Dataflow, the Dataflow graph is compiled to a fixed schedule where every node takes a fixed number of cycles, and the number of tokens consumed is with each cycle is also known in advance. Not all Dataflow programs can actually be expressed within the constraints of synchronous Dataflow, and this is more a general thing that there's different flavors of Dataflow. There's a number of them, including synchronous Dataflow and the various programming languages. I heard LabVIEW mentioned earlier that some of them require that the directed graphs be acyclic. Some of them are not pure Dataflow, like PD with its global variables. But nevertheless, they allow greater and lower amounts of, lesser amounts of expressivity. So if you're going to do synchronous Dataflow, that means you're going to exclude some number of potential Dataflow programs. But it's a powerful technique for creating hard real-time applications. And audio DSP is such an application with hard real-time requirements. So the hard work is all done at compile time. You find a provisional schedule. You simulate execution. You analyze for deadlocks and so on. And then at runtime, there just needs to be pre-allocated space to accommodate a fixed quantity of tokens. There needs to be the node definitions, and there needs to be a mechanism for firing the nodes according to the schedule and actually running the schedule. So again, and that could very well be something that looks an awful like a von Neumann schedule, so you can compile Dataflow down to something which is fairly predictable. But again, this is a hybrid technique. DSP operations like the one in the PD program that I just showed you were typically written in a von Neumann language, but because the higher level program can still be represented as a true pure Dataflow directed graph, we enjoy all the benefits of Dataflow analysis. And this is the thought that I'd like to leave us with this evening. The von Neumann architecture has held on stubbornly and is not going anywhere anytime soon, yet with Moore's law tailing down and new performance coming from additional parallelism, whether that's from cores or clusters, we're all scrambling for ways to adapt our programming paradigms to better take advantage of those parallelized resources. It's been becoming painfully obvious that parallelism, which is not provably correct, does not scale well to complex projects. You inevitably wind up infested with Heisenbugs and other vermin. There are a number of approaches to attack this problem. The functional programming paradigm is one of those, and with the ascendance of multi-paradigm languages, functional programming is more accessible now for working programmers than it has been in the past. Rust's single ownership model, facilitating its much ballyhooed fearless concurrency, is another. Then coarse-grained hybrid Dataflow is another tool in our toolbox, and one which can find utility across many levels. Thank you very much.